So here we need to find the area that is bound between our functions f and g. Okay, so first of all, we should find when they're equal to each other, when they're intersecting. So when is f of x equal to g of x? Or in other words, when is x squared equal to 2x? And by inspection, we can kind of see that that's going to happen when x is 0 and when x is equal to 2. In fact, if we were to plot this and kind of get a visual on what's going on, our linear line, our 2x, is just going to grow linearly like so, and our parabola, or our quadratic there, is kind of going to grow more something like that. So we see we get this intersection here at 0, and we get these guys intersecting at 2. So now if I integrate from 0 to 2, and I do my linear line first, I'll do my 2x, well then I add 1 to the power, divide by the new power, so 2x squared over 2, and I'm doing that from 0 to 2. And if I was to simplify that down a little bit, I just get my x squared term from 0 to 2. So I see here clearly that I'm just going to end up with 4 square units for that linear bit. However, when I integrate my quadratic bit, I'm looking at the x squared term now. So I add 1 to the power, divide by the new power, and I'm doing that from 2 to 0. So I see here that I'm going to end up with 8 over 3 square units here, okay, which is, again, approximately equal to 2.66 recurring square units. But as kind of predicted by our visual, we can see that there is more area underneath our linear line than there is underneath our quadratic line. And that makes sense because our quadratic curve is sat below the linear curve. So for the area bound between the two, for this space in here, we simply just need to take one away from the other. So we do our 4 minus our 8 over 3. Now, instead of writing this as 4, I'm going to write that as 12 over 3. Subtract my 8 over 3, I just end up with 4 over 3 units squared would be the total area that's shaded, bounded between those two curves there like that.